Am I audible? Please raise your hand. Okay, I think I'm audible. I will start class within 2 minutes. I'm waiting for some more students to join the class. At present, there are 36 students joined the class. I will wait for 1 more minute. Still 20 students need to join. The same class video will be uploaded in YouTube. Okay, the URL will be shared through JAMS portal. Last few seconds, I will start the class. Okay, I think I have enough number of students. We were discussing about semiconductors in the previous class. In the semiconductors, I have defined what is the exact meaning of semiconductor, right? And then types of semiconductor. There are two types, intrinsic and extrinsic. Intrinsic semiconductors are the pure type of semiconductors which contain both holes as well as electrons as charge carriers. Similarly, in the extrinsic semiconductor, we have two types. One is N-type semiconductor and another one is P-type semiconductor. In the N-type semiconductor, I have asked the question, what happens to the semiconductor if I add the pentavalent impurity such as phosphorus, right? And everybody was actually not sure about the answer, right? It was given in the notes. You can check it out. If I add the pentavalent impurity, the extrinsic semiconductor become N-type semiconductor. Okay. Pentavalent impurity means one valence electron is added to the semiconductor. Therefore, negative electrons are the majority carriers, and therefore semiconductor will become N-type semiconductor. Similarly, if I add a trivalent impurity such as boron, then you can see this trivalent impurity, let me use the edit option. Okay, trivalent impurity has one electron deficient to form the covalent bond between the four neighboring silicon atoms. Therefore, holes are the majority carriers and semiconductor becomes P-type semiconductor, right? These are the things already discussed in the class. And I have given the definition for majority carrier, minority carrier, and these are only for your understanding sake. I don't think any question will be asked on extrinsic semiconductors in the examination. Okay, and then we have discussed something called as Fermi level in intrinsic semiconductor, right? Fermi level is the highest filled level or highest occupied level at 0 Kelvin, and on an average in intrinsic semiconductor, the Fermi level will lie at the center of the energy gap. Okay, these are the things which were discussed, and I have actually derived this thing, right? EF is equal to half EG. Okay, this is a very important derivation. In the examination, they will ask you to obtain the Fermi energy. I mean, obtain the expression for Fermi energy in terms of energy gap. Okay, and I have given some definitions: energy gap, electron concentration, hole concentration, then carrier concentration, like this, right? And I have also said in the examination, they will just ask you to write down the electron concentration in conduction band. Okay, electron concentration means density of electrons, the number of electrons per unit volume of the material in the conduction band. This expression you have to remember, right? And you have to also mention what are the what is the meaning of all these parameters used in the expression. Okay, mh, me star, ms star, k, t, x square, all these things you have to write. And this derivation relation between Fermi energy and energy gap is already over. Okay, today I obtained the expression for electrical conductivity of semiconductors in terms of, sorry, electrical conductivity of semiconductors in terms of mobility of charge carriers. I will explain what is the meaning of mobility. Okay, someone is actually using their mic. Please mute your mic. Who is that? Please keep your mic closed. Turn off your mic, please. Otherwise, I will remove from the class. I hope everybody can see this PDF. Okay. Now, this is a very important question. Conductivity sigma you have to derive for semiconductors, and maybe 8 marks will be the weightage for this in the examination. Okay. I will start with some statements, and I will construct the mathematical framework for sigma. Okay. And you just try to follow the derivation, very logical derivation, and a few new parameters will be introduced in the expression, just like current density. Okay, current density is the new parameter. I hope you have not gone through this parameter before. And then we have a parameter called as mobility. Okay, mobility of a charge carrier, that is a new parameter which one has to observe in the classroom. Okay, let me start with the statement that I have considered a semiconducting material, a wire of semiconducting material of length L, and area of cross section is given by A. Okay, A is the area of cross section, and I have connected a battery. You can see here. Then obviously electric field due to the battery will be in this direction. It is towards the negative terminal of the battery. And what happens to the electron? Electrons which are present in the semiconductor will move towards the positive of the battery. Okay. Now, this diagram also you have to write in the examination. I hope you are familiar with all the parameters. I have considered a semiconducting material of length L, area of cross section A, and electrons are moving towards the left. Okay, this much information is enough. Now, what is the time taken by this electron to travel the length L is under the question. If the length of the semiconducting material is L, then I will define drift velocity or velocity of electron inside the semiconductor as V or Vd. Okay, V suffix d, that is the drift velocity of the electron inside the material. And therefore, the time taken by the electron will be given as L divided by V, right? You know that velocity V is equal to length divided by time, or you can say time taken by the electron to travel this distance L is equal to L divided by V. Okay, I hope you can digest this formula. T is equal to L divided by V. Okay, now again I repeat once again, T is the time taken by the electron to travel this distance L. Now if I ask you the question, what is the current traveling in the semiconductor? I hope you all know the definition for current. Current is nothing but charges per unit time or charges in motion, right? First thing, we have to calculate the number of charges or number of electrons which are moving in the semiconductor. Okay, so to calculate that, we have to remember the concept of concentration of electron. N of E represents the number of electrons per unit volume of the semiconducting material, right? In the last class, I have discussed that Ne, where Ne represents the number of electrons per unit volume. Okay. You can see I have written here Ne is the electron density. Now, what is the meaning of electron density? Electrons, number of electrons per unit volume, right? If I multiply the energy electron density with the volume, I will get the number of electrons, isn't it? Again, I repeat, Ne is the electron density. That is nothing but number of electrons per unit volume. Therefore, if I multiply electron density with the volume, I will get the total number of electrons, right? Therefore, I know that A is the cross-sectional area of the semiconducting material and L is the length. This product A into L will give the volume of the semiconducting material. Therefore, NeAl, this quantity here, NeAl, this will give the number of electrons inside the semiconducting material. Okay, density into volume will give the number of electrons, right? You have to remember this NeAl, the number of electrons inside the semiconducting material. Now, if I ask you the question, what is the number of charges or total charge inside the semiconducting material? The total charge inside the semiconducting material is the number of electrons into charge of each electron, right? That will give the total charge inside the semiconductor. Okay. NeAl gives the number of electrons into charge of each electron, that is E, will give the total charge inside the cylinder. Okay. Now let us come back to the question of current. Current is nothing but charges per unit time, right? I know now what is the number of charges, that is NeAl into E. This entire thing will give the total number of charges inside the cylinder, and I will divide it by T. That will give me the current. Okay, total number of charges divided by time will give the value of current. Therefore, now I know what is time T, right? Time T is the time taken by the electron to cross the distance L, cross the length of the semiconducting material, and therefore T is given as L divided by V. Now you can cancel L and L. I have L in the numerator as well as in the denominator. Therefore, the expression of current will be this: NeA into EV, right? Where V is the velocity, E is the charge of the electron, A is the area of cross section, Ne is the density of charges inside the volume, okay, inside the unit volume. Now, this is a very important step. Students usually make mistake in obtaining the value of current inside the semiconducting material. Okay, it is NeA into EV. Okay, you have to practice at least 4 or 5 times to perfect this expression. Okay, now let us move forward. Let us move forward. I have obtained current now, right? Now I am interested in obtaining current density. It is a new quantity. I hope you might have not heard the term current density. It is simply current per unit area of cross section. Okay, current density is nothing but current per unit area of cross section. It is similar to your mass density, mass per unit area, mass per unit volume, mass per unit length. You calculate, right? And you will call it as density. Similarly, current density means current per unit area. That's it. Okay. J, current density, I will actually call current density or denote current density as J, and it will be equal to I divided by E. Okay. Now, you know the expression for I. Okay, it is NeA into EV. Substitute the value of I, that is current, and divide it by area of cross section A. You can cancel A in the numerator as well as in the denominator, and you will left with the expression for current density, that is Ne into EV. And let me tell you why we are actually calculating current density. In real situation, current density is the important parameter than mere current. Okay, current density is current flowing across unit area. If the unit area is bigger, current density will be smaller. Okay, therefore uh, to measure the extent of current flowing inside a material, okay, to actually measure the impact of the current, we require the measurement of unit area of cross section. You cannot send a very big current in the thin wire, right? Therefore, you require to define this quantity known as current density. Okay, current per unit area. You will actually understand once you get into the practical situations. Okay, we have to be aware of current density inside the material. Okay, you cannot use a very thin wire and pass very high current, that will burn down, right? Therefore, in practical application, usually current density was actually involved than current. Okay, somehow let us move forward. Now I have obtained the expression for current density, that is NEV. I will call it this as equation 2. Now I will introduce one more new concept, that is known as mobility of electron. Okay, mobility is nothing but it is drift velocity per unit electric field. Okay, in the semiconducting material or any conducting material, while defining uh, the speed of the charge carrier, for example, speed of the electron, instead of its drift velocity, it is useful to define its mobility. Okay, uh, that is because if we have very dense atmosphere for the free electrons, it will very difficult for the electron to travel the distance. Okay, no matter what kind of vehicle you are riding, it is the traffic which actually guides your speed, right? The same concept is also used in defining the speed of the electron inside the material. You can see this mobility is directly proportional to velocity, but this mobility is inversely proportional to electric field. Okay, if the material is, if the electron is moving with a brisk speed at very small electric field applied, if the electric field is very small and the electron is moving with a higher speed, then its mobility is good. And similarly, if you require a very huge electric field, then the mobility of the electron is very small. This kind of, this is the actual importance of defining this mobility. Okay, let me try once again. I will try to explain it with some other example. Mobility is something like which actually decides how much speed that an electron can get inside the semiconducting material for the applied, with respect to the applied electric field. If you apply very small electric field, then also very good current is flowing, then we can say the electron will have very high mobility. Okay, it actually tells about the motion of charge carrier, how freely or how difficult for the charge carrier to move inside the material. Okay, I will try to explain with some other examples in the classroom during offline classes. Okay, for now, let us stick with the basic definition of mobility. That is, mobility is nothing but drift velocity per unit electric field. Okay, if the electric field required is higher, then mobility of the charge carrier is very less. If the less electric field is enough for the charge carrier, then its mobility is very good. Okay, uh, therefore I can write velocity of the electron in terms of mobility as v is equal to mu e into e. Okay, therefore this expression for electrical current density will become Ne E into, in the place of V, I will write mobility of electron into E. Okay. Therefore, current density is now Ne E into mu E into E. Okay. Similarly, this same current density can also be written as sigma, that is electrical conductivity times applied electric field from Ohm's law. J, current density, can be written as sigma E into E. This is actually derived from the regular Ohm's law. I hope you all know the equation which relates voltage with current. What is that equation called as? That is nothing but Ohm's law, right? V is equal to I into R. This Ohm's law can also be written as J is equal to sigma into E. Okay, I will try to explain it. Okay, I cannot, I am not able to write R here. Okay, let me try to write R. Okay. V is equal to IR, right? This V is equal to IR can also be written as J is equal to sigma E. Just divide the left hand side by area. Okay, R. Okay, I will show you in the offline class how I can obtain V is equal to, how I can obtain J is equal to sigma E from V is equal to IR. I just want to divide the left hand side by area and multiply the right hand side with length and again divide by area. Then I will get J is equal to sigma into E. Okay, I will show in the online, I will show in the offline class how can I obtain this V is equal to IR. How can I obtain this J is equal to sigma E from V is equal to IR. Okay, for the moment, just understand J is equal to sigma E is nothing but Ohm's law. In the place of current, I have current density. In the place of voltage, I have electric field. In the place of resistance, I have the inverse of resistivity, that is conductivity. Okay, you can also find on your own, but I will definitely show how I can obtain J is equal to sigma E from V is equal to IR. Now just compare these equation 3 and equation 4. You will get, if I compare J is equal to NE into mu E with J is equal to sigma E into E, you will get the expression for sigma E. Okay, if I compare these two equations, equation number 3 and 4. Okay, I can cancel J and J on the left hand side and E on the right hand side. Therefore, I am left with sigma E is equal to NE E into mu E. Okay, isn't it? If I compare these two equations, I can get the conductivity due to electrons as Ne E into mu E. Okay, this is the expression for electrical conductivity if I consider only electrons are the majority carriers. Okay, if I consider a intrinsic semiconductor where I have equal number of holes, therefore the conductivity is also due to the holes, and that expression, the conductivity due to holes, can be given as NH into E mu H. Okay, it is just derived. You need not to derive this sigma H or conductivity due to holes. You can compare the expression for conductivity of electrons, and you can tell in the place of electron density, you have to substitute hole density, and charge of each hole is same as charge of electron E. And in the place of mobility of electron, I have to substitute mobility of hole, right? Now, in intrinsic semiconductor, I know that the conductivity sigma is due to both electron and hole, right? And therefore, the conductivity sigma can be written as Ne E mu E plus Nh E mu H. Okay, this is the sum of conductivity due to hole and conductivity due to electron. This is the expression which you have to derive in the examination. And I have also mentioned that in intrinsic semiconductors, number of electrons is same as number of holes, and I will call them as Ni, where Ni is the intrinsic charge concentration. Okay, therefore this expression, final expression for electrical conductivity, can be written as I can take E common, right? In the both expression, I have E as common. That is, charge of the electron is same. And in the place of NH and Ne, I will substitute Ni, intrinsic concentration. Okay. And what are the things left? I have mu E and mu H. I just add mu E and mu H. Okay. This will finish up the derivation. Okay. If you obtain this expression, you will get definitely 8 marks. Okay. I will once again summarize the derivation which I have actually done in this class, and I will wind up the class. Okay. Again, I repeat, this is a very important derivation. In the examination, they will ask you to obtain the expression for electrical conductivity of semiconductors. And please make sure you read the word semiconductor here, because in the conductor part also there is the expression for electrical conductivity. Don't interchange the derivations. Okay. For semiconductors, you have slightly different derivation for conductivity. For conductors, you have slightly different. Okay. Therefore, please make sure you read this sentence properly. Okay. Electrical conductivity of semiconductor. Okay. Very simple derivation, but at least 4 or 5 times you have to write and practice. I once again show. I have started with a cylindrical material of semiconductor of length L, area of cross section A. I have connected a battery, and you know that the electrons will move from negative terminal of the battery to the positive terminal. This is the direction of electron motion. Okay. And the time taken by the electron to travel this distance is given by L divided by V. Okay. It is natural. I find T is equal to L divided by V, where V is the drift velocity of electron. And I have also calculated the number of charges inside the semiconductor. Okay. Number of charges inside the semiconductor is given by the product of density of electron and volume into charge of each electron. That is, NeAl into E will give the total number of electrons inside the semiconducting material. And from the definition of current, I know that total number of electrons divided by time will give the current. I know the expression for time in terms of velocity and length. It is L divided by V, and therefore I have obtained current as NEA into EV. Okay. And then I defined a new quantity known as current density, that is current per unit area, and I have obtained it as NE into EV, right? And then I have expressed velocity in terms of one more new quantity called as mobility, okay, which actually tells about the speed of electron inside the semiconductor, okay, per applied unit electric field. Therefore, this drift velocity is given as mu E into E. In terms of drift velocity, in terms of mobility, I can write current density as J is equal to NE into mu E. Therefore, from Ohm's law, I can say J is equal to sigma into E, right? It is nothing but the another version of V is equal to IR. Okay. It is a task for you guys to obtain J is equal to sigma E from V is equal to IR. Okay. If you are not able to obtain, I will do in the class. I have to now compare these two expressions. J is equal to NE E into mu E with J is equal to sigma E into E. On comparison, I can find out that sigma E, the electrical conductivity due to electron, is nothing but NE E into mu E. Okay. And similarly for holes, sigma H, the electrical conductivity due to holes, is given as NH E into mu H. The concentration of hole, charge of each electron into mu H, mobility of hole. And as you know that number of charge carriers, that is electrons, and number of holes are same in intrinsic semiconductors, I can replace Ne into Ne and NH by Ni is something called as intrinsic charge concentration. Okay, and stating that sigma is the sum of sigma E and sigma H, and replacing Ne and NH as Ni, I can obtain the final expression for conductivity as Eni into mu E plus mu H. Okay, practice once again in the free time, and try to repeat it or reproduce it on your own. If you are not able, then please ask me. I will derive once again. Okay, and I definitely do these classes in the offline mode also. Okay, therefore don't panic if you are not able to understand the derivation in the online class. Okay, uh, my time is running out. Please ask me the doubts personally as well as. Okay, thank you very much for the participation. I hope I have given the notes and you are circulated it. In the next class, I will do a concept of this Hall effect, and I will wind up the semiconducting part. Okay, semiconductor part. I again thank you all, guys. It's only a 40 minutes class. Okay, and I think I have done justification. Okay, let me stop the sharing. Okay, I will end the class now. Thank you for participating.